Friends, today we are now going to discuss Fourier transformation. So, it's a very important topic in case of mathematical physics or in case of quantum mechanics and in case of physics also. It's very important topic. So, let's discuss how Fourier transformation, how the concept of Fourier transformation is coming. So, first start, introduction to Fourier transformation. So, whenever we are discussing classical mechanics, when we will discuss classical mechanics, okay, what we discuss? We discuss that Hamiltonian is function of position and momentum. Yeah. And in case of phase space trajectory in the classical mechanics, we draw the phase space trajectory x, p, x, y, p, y, z, p, z. Okay. But in case of quantum mechanics, whenever it is the case of quantum mechanics, then concept of phase space trajectory, is invalid. Because why? Because of uncertainty principle. But why? Because according to uncertainty principle, position and momentum cannot be measured simultaneously. That's why phase space concept is invalid in case of quantum mechanics. So here it will come the concept of Fourier transform. So why it will come the concept of Fourier transform? Because we can describe the motion of particle separately in position space and momentum space. If we know the motion of particle in position space, then we can describe it in momentum space. Means, in quantum mechanics, suppose you are describing the motion of particle in x space, means position space. Suppose you are describing the particle motion in position space. Okay, that's nice. But if you are wishing to do the motion of the particle in the momentum space, means whenever you are describing the motion of a particle in position space, and now you are wanting to describe the motion of the particle in momentum space, position space to momentum space. Then you need to do Fourier transform. Yeah. In that case, Fourier transform will be come, because whenever we are describing the motion of the particle in k space, actually momentum space is in general momentum space will be described by k space or momentum space. So whenever we are going to describe the motion of the particle in k space, we need to do that Fourier transformation. So formula for Fourier transformation in 1D, in one dimension, formula for Fourier transformation will be what? Suppose in x space or position space, function is f of x. So in momentum space, how we will write this f of x? So in momentum space, Fourier transformation of f of x is, the mathematical definition of Fourier transformation will be 1 by root 2 pi integration minus infinity to plus infinity f of x e to the power iota kx dx. Let me write clearly. So Fourier transformation of a function f of x is given by 1 by root 2 pi. Let me write with good handwriting, otherwise you can't understand. 1 by root 2 pi integration minus infinity to plus infinity f of x e to the power exponential of iota kx dx. So this is the mathematical definition of Fourier transform. Someone keep this constant 1 by root 2 pi. In some books you will see that this constant is understood So it doesn't matter actually. So where k is wave vector, k equals what? P equals h cut k. So k equals p by h cut. Momentum, it is having the dimension of momentum actually. So in 1D, it is a formula for in 1D case. And it is the general definition of Fourier transform in 1D case. So general definition of Fourier transform in 3D case, what it will be? In 3D, Fourier transformation will be 1 by 2 pi whole to the power 3 by 2 integration minus infinity to plus infinity f of r vector, here f of r vector e to the power I k dot r d tau. Yeah. So e to the power minus infinity to plus infinity in 3D, it can be written as 1 by 2 pi whole to the power 3 by 2 f of r equals 1 by 2 pi whole to the power 3 by 2 minus infinity to plus infinity f of r vector e to the power I k dot r d tau. So let's take an example by which I will describe more clearly the introductory part of Fourier transform. Suppose you have an wave function, you have a function, constant function a, f of x equals suppose a, let's take a, and limit is mod x less than equals a. Let me write clearly. You have a function f of x that is mod x less than equals a range, okay, and 0 that is x greater than a range. So whenever you are wanting to do the Fourier transformation of this, how it will be described graphically. So how this function will be described graphically in position space? Whenever in position space you will describe this function, it is just a constant function minus a to plus a, okay, f of x. It is position space. In position space, just this line minus a to plus a, this range mod x less than equals a means minus a to plus a. This function f of x is constant. It is described in position space. So if someone asks you to describe this in the momentum space, how you will describe this? So describe this in momentum space, we will describe in such a way: Fourier transformation of f of x 1 by root 2 pi integration minus infinity to plus infinity f of x e to the power iota kx dx. 1 by root 2 pi, here wave function is such that function equals a within minus a to plus a. So here it will be a e to the power iota kx dx, and greater than a x greater than a, that will be 0. So that has no effect. So after calculating this, we'll get f of x, Fourier transformation of f of x equals 1 by root 2 pi integration minus a to plus a e to the power iota k, iota kx dx, or here you will write it, as in such a way: a by root 2 pi minus a to plus a e to the power iota kx dx. So integration iota kx dx. So after solving the integration, we'll get e to the power iota k minus e to the power minus iota k divided by iota k. Okay. So after solving the whole part, you will get root 2 by pi small a into a sin k by k of a. This thing. So let me write clearly the result. In the position space, we are writing that f of x equals a for mod x less than equals a, and 0 for x greater than a in the position space. And in the momentum space, what we get? The momentum space, let's call it f of k, we will get root 2 by pi a of a sine k a divided by ka. Okay. So what's the difference actually in positions, in the position space? In the position space, whenever we are describing it in the graphical way, we are getting what? We are getting a constant line a, that is f of x minus a2 plus a, and whenever in the momentum space, what we have got? Sine k by k, that means we will get like an wave packet, sinusoidal wave packet. So this is the beauty of that. See, this is the beauty of that Fourier transformation. Can you notice that in the position space we are getting such a constant function f of x equals a, but whenever we are drawing it in the case of momentum space, we are getting such sinusoidal wave packet. So this is the case of Fourier transformation. In such a way we can describe the position space wave function, position space x space or position space function, into a momentum space function. So this is the introductory part of the Fourier transform. So in the part 2, I will describe the properties of Fourier transform. So properties of Fourier transform. So to get that, you have to stay tuned. So that's it for today. That's it for now. Thank you. Bye. Because in the next part, I am bringing that properties of Fourier transformation. So thank you so much for patiently watching my video.